Lecture 7 in number theory. And I want to go over homework assignments that we've had so far. We finished chapter 1, but before we start chapter 2 on congruences, I want to make sure that people see how to solve different kinds of problems that we've had. So in chapter 1, we've covered the first 5 sections, and the homework so far has been from sections 1, 2, and 3. So let's take a look at some of those problems. So this is going to be going over homework problems. So section 1.1 was on the division algorithm. And part of this is just to do some simple calculations. Find all divisors of a number, for example, or find the quotient and remainder when the number is divided. One number is divided by another number, or to write the M-adic representation of an integer. So for example, in problem 4A, well, let's say 4D, this is just long division. Find the quotient and the remainder when you take the number A equal to 291 and D equal 12, and you divide. So this is just asking you to do what you did in elementary school. 12 into 291, 2, 24, 51, 4, 48, 3. So the quotient Q is equal to 24. The remainder R is equal to 3. And the division algorithm, when written out nicely, says 291 is equal to 12 times 24 plus the remainder of 3. So please interrupt if there are any questions about any of these problems. Let's look at number 6. In number 6, we have the number 526, and we want to write it. We want to write the M-adic representation for different number values of M. So for example, find the 7-adic representation of 526. So we have to look at the powers of 7. 7 to the 0th power is 1. 7 to the 1st power is 7. 7 squared is 49. 7 cubed is 343. And 7 to the 4th power will already be too big. 7 to the 4th power, if you want to do it quickly without actually a lot of calculation, that's 7 squared squared. That's 49 squared. 49 is 50 minus 1. So you know how to square a binomial. This is 2500 minus 100 plus 1, which is 2401. That's 7 to the 4th. So that's already bigger than 526. So we only have to look at powers of 7 up to the 3rd power. And what is 500? And 343 clearly goes into 526 just one time. 526 minus 343 is what? 6 take away 3 is 3. 12 take away 4 is 8. 4 take away 3 is 1, is 183. So 526, the highest power of 7 less than this or no greater than this is the third power, 343. You subtract, you get 183. Highest power of 7 less than 183 is 49. 49 goes into this 3 times. 3 times 49 is 147. 183 minus 147, I think that's 26.
Is it 26 or 36?
13, let's see, 183. It's 36. Thank you, 36. 36. 36, the largest power of 7 less than 36. That's 5 times 7 plus 1. So if you put this all together, 526 is 343 plus 183, which is 343 plus 3 times 49, 147, plus 36. This is 343 plus 147 plus 35 plus 1. So in terms of powers of 7, 526 is 1 times 7 cubed plus 3 times 7 squared plus 5 times 7 to the first power plus 1 times 7 to the 0 power. So this is, if I did my arithmetic correctly, the 7-adic representation of 526. Okay. Problem 9, which is closely connected to problem 8, so then we do both of them, is the following. So for problem number 8, prove that if n is even, then 4 divides n squared. So the proof is easy. If n is even, n equals 2k for some integer k. So n squared is 2k squared, is 4 times k squared. So 4 divides n squared. That's the complete proof. Problem 9 is to prove that if n is odd, then 8 divides n squared minus 1. So the proof is very similar. If n is odd, n is 2k plus 1 for some integer k. So n minus 1 is, actually, let me do it better, a better way than that. So if n is 2k plus 1, then n squared is 2k plus 1 squared. If you square this, you get 4k squared plus 4k plus 1. From these first two terms, I can factor out a 4k. This is 4k times k plus 1 plus 1. So n squared minus 1 is 4k times k plus 1. So this is clearly divisible by 4, but what we want to show is divisible by 8. So we make the following very important observation. K times k plus 1 is always an even number, because either k is even, k is divisible by 2, so this is even, Or k is odd, but then k plus 1 is even. So k times k plus 1 is 2 times L for some integer L. So this is equal to 4 k times k plus 1, 4 times 2 times L, or 8L. So n squared minus 1 is 8L. That means 8 divides n squared minus 1. So for example, if you take an odd number, say n equal to 11, n squared is 11 squared is 121. That's 120 plus 1. 120 is 8 times 15 plus 1. So n squared minus 1 in this case is 8 times 15 divisible by 8. Any questions about this?
I did it different. I chose n to be 5, and then I did n squared minus 1 over 8. Then 5 squared is 25 minus 1. It's 24 divided by 8. I get 3. It's still the same.
Well, that's an example, but it's not a proof. Right? You prove that the statement is true for n equal 5. This shows, my example shows the statement is true for n equal 11. But the problem is to show that it's true for all odd numbers. Just giving some examples is never a proof. It's often very good to do examples and you get an idea about how to put together a proof, but it's not a proof. Do you understand the difference? This,
No.
well, this is a
That's
proof,
the proof.
right? This is a proof. This is an example. Choosing n equal to 5 and computing n squared minus 1 over 8 and getting 25 minus 1 over 8, which is an integer 3, is another example. But if you put this, if I asked you to prove, if this was a problem on the exam, prove that if n is odd, then 8 divides n squared minus 1, and you put down this example, you would get 0 credit because it's not a proof. It's just one instance of the general theorem. Right? So this is a proof. This is an example. This is not an incorrect statement, but it's not a proof. It's not an answer to the question.
So, how did you do 2k plus 1? How did you just chose 2k plus 1 as
No, I
n?
didn't just choose it. Prove that if n is odd, every odd number, the definition of an odd number is a number of the form 2k plus 1 for some integer k. This is the definition of an odd number. This is what odd means. An integer is odd if it can be written in the form 2k plus 1. That's the definition of an odd number. 5 is an example. 5 is 2 times 2 plus 1. 11 is an example. 11 is 2 times 5 plus 1. 101 is an example. 101 is 2 times 50 plus 1. But these are just examples, right? If n is odd, the definition of odd is a number of the form 2k plus 1. So if you take n and you square it, you get 2k plus 1 squared. Which is 4k squared plus, then this is the argument. But this is a proof that applies to every odd number. An example is just an example of one particular number, and it doesn't prove anything at all. Right?
Okay, plus 1. So if you just put that the proof the example of the odd.
This example,
No.
This.
The one at the top. If you just put that
All right,
on the
when you say the
exam,
one at the top, what do you mean?
the n equals 2k plus
Right,
1,
that's not an example. That's a proof.
the proof.
Right? This is a proof. This is an example. They're two completely different things. Okay. This is a
But I
proof.
don't understand
But
how you solved it, how you solved the problem.
it's exactly, so let's just go through what's written. If n is 2k plus 1, n
Mhm.
squared is 2k plus 1 squared. That's 4k squared plus 4k plus 1, and you square it. And if I factor 4k from the first two terms, that's 4k times k plus 1 plus 1. So n squared minus 1 is 4k times k plus 1, right? This is my first conclusion from this argument. This says, if you look at it, that 4 divides n squared plus 1. But the
N
problem
square
is,
minus 1.
what?
Says n square minus 1, right?
Yeah, 4 divides n squared minus 1. Right? But the problem is to prove that 8 divides n squared minus 1. So I have to look at this more closely. And when I look at this, I observe that k times k plus 1 is always an even integer, because either k is even, but if k is odd, k plus 1 is even. So one of these two numbers is even. The product of two numbers, if one is even, then the product is even. So k times k plus 1 is even for all k, all integers k. And the definition of an even number is one which is 2 times something. So take k times k plus 1 is equal to 2 times L for some integer L. So I can replace k times k plus 1 by 2L. So I get n squared minus 1 is 8L, which means exactly that 8 divides n squared minus 1. That's the proof.
Why you replaced it with 2L?
Because I need to show n squared minus 1 is divisible by 8. How do I know that n squared minus 1 is divisible by 8? I have to prove that. This is the problem. Prove that if n is odd, then 8 divides n squared minus 1. This is what you have, this is what you're required to learn in this course, in almost any 300 or 400 level math class, how to prove mathematical statements. This is a proof. These are examples. These are not proofs. On an exam, this would get you 0 points. 0, because it's not a proof. This is a proof. Okay? So learning how to prove things is something you need to do in mathematics. Let's do another example, which has a proof. Problem 12 was on the homework. Problem 12 is prove that if D divides A and D divides B, then D divides AX plus BY for all integers X and Y. So I could give an example, but an example is not a proof. Here's an example. Suppose I take D equal to 7, A equal to 21, and B equal to 35. So 7 divides 21, and 7 divides 35. Suppose I let x equal 4 and y equal -2. I'll make x equal 6. It's more interesting. Suppose let x equal 6 and y equal -2. So in that case, what is the number ax plus by? So ax plus by is 21 times 6 plus 35 times -2. Let's see, 121 times 6 is 126. Minus 70 is 56. It's 56 divided by 7. Yeah, it's 7 times 8. So for these choices of A, B, X, Y, and D, D divides A, D divides B, and D also divides AX plus BY, which is 56. So this is just an example, just so you understand what the assertion of the problem is. So this is an example, it's not a proof. How do we give an actual proof? Well, so if D divides A, that means that A is dk for some k, some integer k. And if D divides B, then B is D times L for some integer L. And if you take any integers x and y, ax plus by is what? A is dk, so this is dkx. And by, b is dl, so that's dly. So ax plus by is dkx plus dly. I can factor a d out. I get d times kx plus ly. So this integer times this integer is ax plus by. So d divides ax plus by. And that's a proof. Okay. Any questions about this? This is mathematics. This is what we have to do.
How is this one different from the other one we just did?
How is this proof different from the other proof?
Yeah.
They're completely different. You're proving different statements. Here's the statement we're trying to prove in this case. This is one statement. Prove this, that if D divides A and D divides B, D divides AX plus BY. That is, that's different from proving that if a number is odd, then if n is odd, that n squared minus 1 is divisible by 8. They're two different statements. What's the difference between proving the derivative of x squared is 2x and that the integral of x squared is x cubed over 3? Well, they're two different things. They're two unrelated statements. They're proofs, and they're different proofs. And how do you come up with a proof? You have to use your creativity, imagination. And You have to have studied the proofs that are in the book and learn the techniques that have been used, so you can apply those techniques to other problems. Right? That's what you have to do. What about number 17?
Hello, Professor.
Yes,
Hello, see, on the exam, you have to prove the theorems in the textbook. I think what you did in the class, or
well, sometimes, but sometimes I'll ask you to prove something you haven't seen before, where you have to use the techniques. It's no different from, in calculus, suppose you take an exam and they ask you to differentiate, 100x to the 6 plus 25. Well, that particular problem you never saw before, but you've learned the techniques to solve that problem, and you apply those techniques. So it's the same with proofs. You study the proofs in the book and the proofs in the lectures, and you learn the techniques for giving proofs. So when you have to prove something new, you're able to do it. Right? I mean, when you take a calculus test, you don't get problems that are exactly the same numbers as the examples in the book. They're related, but they're different numbers, different problems, and it's the same here. This is what you have to learn. Right? Let's look at problem 17. One technique for proving theorems is mathematical induction. You absolutely have to learn what an induction means and how to prove something using mathematical induction. So problem 17 is prove by induction that if you take the sum of the first n cubes, you get exactly what you get by taking the sum of the first n numbers and squaring it. So let's take an example. This is not a proof. This is just an example. You do this to convince yourself that the statement is true. Suppose n is 4. So on the left-hand side, I have 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed. That's 1 plus 8 plus 27 plus 64. If you add that up, what do you get? What do you get? What's the sum?
100.
100. Okay. And if you add 1 plus 2 plus 3 plus 4, what do you get?
10.
10. So if you square 1 plus 2 plus 3 plus 4, you get 10 squared. What is 10 squared?
100.
100. So if you look at this example, 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed is 1 plus 2 plus 3 plus 4 squared. So this is just an example of this statement in the special case n equal 4. Let's just do another example just to encourage you to think this is correct. Suppose I take n equals 6. So I have 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed plus 5 cubed plus 6 cubed. So what are the first 6 cubes? 1 plus 8 plus 27 plus 64. What is 5 cubed?
125.
What is 6 cubed?
216.
Okay, and if I add up these 6 numbers, what do I get?
$441.
441. Okay. And on the other hand, if I add up the numbers from 1 to 6, if I add up the first 6 integers, what do I get? What's the sum of the first 6 integers? What is it? Someone tell me.
20.
No,
21.
21. So if I square the sum of the first 6 integers, that's 21 squared. What is 21 squared?
441.
441. Exactly the same thing. So 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed plus 5 cubed plus 6 cubed is equal to 1 plus 2 plus 3 plus 4 plus 5 plus 6 squared.
Wait, is it true for any number?
Well, that's what you have to
Just-
prove. The problem is to prove that this is true for every positive integer n. This is the statement that you're asked to prove. When you're given a statement like this, that's what it means. Prove that it's true, not just for 4 and not just for 6, but for any number, right? If n is 1,000,000, it has to be true. You wouldn't check it by hand, but you can prove, you have to prove that it's true, even though the numbers are pretty big. That's what a proof is.
Okay, so how we prove it now?
Okay, so you have to know what it means to prove something by induction. Let me start with a simpler example. This was number 16. Problem number 16, the one just before this, said, if you just take the sum of the first n integers, that's always equal to n times n plus 1 over 2. And the previous problem was to prove by induction. I did this in class, that this statement is true. And again, you can check some simple examples. If n is equal to 1, on the left-hand side, you get 1. On the right-hand side, you get 1 times 2 over 2, which is also 1. If n is 2, on the left-hand side, you get 1 plus 2. On the right-hand side, you get 2 times 3 over 2, which is 3. And 3 equals 3. These are equal. You take n equal 3 just to see, make sure everything is correct. 1 plus 2 plus 3 is 6. 3 times 4 over 2 is 6. It works. And then you have to prove by induction this is true for all n. So proof by induction.
Wait, for n equals 2, why did 1 plus 2 equals 3?
1 plus 2 equals 3. Why? You're asking why is that true?
No, because the one before n equals 1, you put the 1 here equals 1 times 2.
Right. What you're putting on the right-hand side is n times n plus 1. So if n is 1, n plus 1 is 2. If n is 2, n plus 1 is 3. If n is 3, n plus 1 is 4. N times n plus 1 over 2. That's what you're doing. That's what this formula means. So if you want to prove something by mathematical induction, first check the case n equal 1. For n equal 1, I already did this. 1 equals 1 times 2 over 2. So the statement is true for n equal 1. And in induction, then you say, assume the statement is true for some integer n. And then you have to prove it for the next number, n plus 1. So if it's true for n, this means 1 plus 2 up to n equals n times n plus 1 over 2. And what you have to, so this is given then. This is given for a particular n. What does it mean to prove it for n plus 1? You take the sum of all the numbers up to n plus 1. But the sum of the numbers from 1 up to n plus 1 is the sum of the numbers from 1 to n plus n plus 1. And by hypothesis, by the induction assumption, the sum of the numbers from 1 to n is n plus 1 over 2. And I'm adding n plus 1 to that. So this plus this. And then I want to simplify this expression. I want to put it over a common denominator. These are just adding fractions. So you have to know sort of this sort of high school algebra. I can write n plus 1 is 2 times n plus 1 over 2. So now I can add these fractions because they have the same denominator. This is n times n plus 1 plus 2 times n plus 1 over 2. What is that? If I factor out the n plus 1, this is n plus 1 times n plus 2 over 2. And of course, n plus 2 is just n plus 1 plus 1 over 2. So this algebraic expression is what you would get from this if you replace n by n plus 1. And this is true. The sum of the first n plus 1 positive integers is this. So that's a proof by mathematical induction. I mean, this is something that you absolutely positively have to learn to pass a course in number theory. I mean, giving simple arithmetical proofs like this.
Hello, Professor.
Yeah,
Why do you do n plus 1 plus 1?
because I want to show that this statement is not only true for n, if I want to prove that if it's true, I want to show that it's true for n plus 1. So if I replace n by n plus 1, on the left-hand side, I have the sum of the integers up to n plus 1. And on the right-hand side, I have n plus 1 times n plus 1
Oh, yeah,
plus
okay.
1.
Okay. Thank you. Actually, wait, it says, it says over there n plus 2 before that. What is that?
N plus 2. What do you mean, what is it? N plus 2 is n plus 2. So this is just a string of equations, equalities. This equals this, equals this, equals this. How did I get from here to here? I factored out n plus 1. If I factor out n plus 1, I'm left with n plus 2.
Oh, okay. Yes.
So this is an example of a proof by mathematical induction.
Can I see that last page? I didn't finish writing. Professor, can I see that?
There.
Oh wait, Professor,
Yeah,
I think in the previous step, it's n times n plus one plus two times n plus one. But why does the n disappear at the end? Then
what, no end
Okay.
disappears. What are you talking about?
no, I mean I don't get how that becomes n plus one times n plus two.
So
I'm getting confused.
do you see that how I got to this step?
Yeah. That's it.
Okay, so here I have n times n plus one.
Yeah.
Here I have 2 times n plus one.
Okay.
If I factor out the n plus one, I get n plus one times n plus two.
Okay. Okay. And then at the last step, you put n plus one times n plus one plus one. What is n plus one plus one?
N plus
Is that-
two. 1 plus 1 is 2.
Oh, okay, okay, okay. Now I got
Right.
it.
Right.
Thank you.
If it only comes down to knowing that 1 plus 1 is 2, everything's pretty easy.
So
this-
that's the answer, n plus one.
It's not an answer. Have to be careful.
That's the proof.
Not a problem where you have to get the answer. It's a theorem where you have to give a proof. So this is a correct proof of this of the theorem.
Okay.
Right? Okay. So what I just proved is that the sum of the first n integers is equal to this. And let's go back to problem number 17. Prove for every integer n, 1 cubed plus 2 cubed plus 3 cubed, all the way up to n cubed, the sum of the first n cubes is the sum of the first n integers all squared. That's what you have to prove. And this is true for n equal 1, because 1 cubed is equal to, because you only have one number on the left, 1 cubed. You only have one number on the right, 1 squared, and 1 cubed equals 1 squared, right? They both equal 1. So this statement is true for n equal 1. And I already checked some other examples where it was true for n equal 4 and for n equal 6. I just, for fun, I did those examples. But now I want to prove this is true in general. So now we assume it's true for some number n, and we must prove the statement for n plus 1. So I look at the sum, not of the first n cubes, but of the first n plus 1 cubes. I look at this. And the sum of the first n plus 1 cubes is the sum of the first n cubes plus n plus 1 cubed. And by the induction assumption, because I'm assuming this is true for some particular number n, I can write this as 1 plus 2 plus 3 up to n squared plus n plus 1 cubed. That is, this I can replace with this, because I'm assuming that they're equal. But here I have the sum of the first n numbers, and I wrote a formula for that. This thing in parentheses is n times n plus 1 over 2. So this is n times n plus 1 over 2 squared plus n plus 1 cubed. I'm replacing this sum with this. And what is this equal to? This is equal to n squared, n plus 1 squared over 4, right? If I square this, this is what I get. Plus n plus 1 cubed.
Wait, where you get the n times n plus one over 2 squared?
I have the sum of the first n numbers squared,
Mhm.
right? Do you see where I got this?
Yeah, from the question.
Okay.
Yeah.
And what's the sum of the first n numbers? N times n plus 1 over 2. So I can replace this by n times n plus 1 over 2. So I got from here to here by using this previous result.
Okay.
And when I square this, I get this. Right? 2 times 2 is 4. And from this, I can factor out n plus 1 squared. If I factor out n plus 1 squared, I get n squared over 4 plus n plus 1. Right? Because n plus 1 cubed is n plus 1 squared times n plus 1. And you have to know fractions. If I put this over, if I add these two fractions, I get n squared plus 4 times n plus 1 over 4. Right? 4 over 4. So this is n plus 1 squared. This is n squared plus 4n plus 4 over 4. And again, you have to know high school algebra. You have to know factoring. This is n plus 1 squared, and this is n plus 2 squared over 4, which is the same as 2 squared. 2 squared is 4. So this is equal to n plus 1, n plus 2 over 2 squared. Which is exactly, by this formula, the sum of the first n plus 1 numbers squared. And that's the proof. Mhm. This is the proof. This is just a little
Square
side.
over 4.
Yeah.
Wait.
This is the algebra involved in the proof.
How you got the n squared over 4? You separated the n times n plus 1 over 2 squared.
Where, from here?
Yeah.
So I have n plus 1 squared. Here I have n plus 1 cubed, right? N plus 1 cubed is the same as n plus 1 squared times n plus 1. That's the definition of a cube. So if I factor out n plus 1 squared, I'm left with n squared over 4 plus n plus 1. That's what I have here. N squared over 4 plus n plus 1. Take away, factor out the n squared, n plus 1 squared, you're left with n squared over 4.
Hello, Professor?
Yeah,
I can't see the last part. Like the last
this is the last part. That's the
yeah,
end.
I can't see. Is there any way you can tilt the paper, move it up? So I can
Well, no, it's on this. I can see, if I see it on my screen, you You see
Oh.
exactly what I see on my screen. Do you see my pen?
Oh yeah, okay. Now, okay.
That's
Now I
the
see.
this little square means end of the proof. Okay. Let's look at some problems in section 1.2 on the greatest common divisor. Let's just start with number 1. Compute 935, 1122 in parentheses. This means the greatest common divisor of these two numbers. So I don't know. How do you find the greatest common divisor? This number is not divisible by 2. This number is not divisible by 3. You can check that quickly. This is not divisible by 5. I don't know. Is this divisible by 7? So I could do this quickly using the Euclidean algorithm, but without using the Euclidean algorithm, let me just see if I can do it in just by trying. So this is the GCD, right? The greatest common divisor. If I divide 7 into 935, does this go?
Go, Ram.
No. So this is not divisible by 7. What's the next prime? 11. Suppose 11 into 935. This goes 8 times 55. Yeah. So 935 is 11 times 85. Does 11 go into 1122? So 11 into 1122, this goes once. 0, 2. So 1122 is 11 times 102. 85 is small enough that I can factor it. 85 is 17 times 5. 102 is 2 times 51. Let's see, what is that? 51 is 3 times 17. So if I have 935 is this, and 1122 is this, the greatest common divisor is going to be 11. Eleven divides both of those numbers, and
How about 187? Because I for
187. What is
Yeah.
where did you get 187?
1122 equals 935 times 1 plus 187.
No, that's the remainder. The greatest common divisor is the largest integer that divides both of these numbers. So that largest integer is 11. Nothing bigger than 11 divides those numbers. Now, if we jump ahead to the next section, and we want to use the Euclidean algorithm, then we would do what you said is the first step. 1122 is 1
Good.
times 935, and it leaves a remainder
187.
of 187. 935, if you divide it by 87,
Times 5,
what's 5 times 187?
935.
935. Oh, so let's
Plus
see what
7.
happened here. Oh, I'm sorry. I mean, wait a minute. No. So, oh, sorry. I mean, I had the answer here, but I didn't look at it right. 935 is 11 times 17 times 5. 1122 is 11 times 2 times 3 times 17. So I have 11 and 17 here. So the greatest common divisor is 11 times 17, which is 187. Thank you. And that's exactly what the Euclidean algorithm shows. So the GCD of these numbers is 187.
Yeah. That's right.
Let's look at another problem. So you're very good at doing numerical problems, but you have to learn how to do the proofs as well.
Yeah, proofs are really hard for me to
Yeah,
understand.
so that's what you need to concentrate on.
Yeah. I really need help on that proof.
Yeah, let's look at number 3. Number 3 looks like a hard numerical problem. Find integers x and y such that 13x plus 15y equals 1. Huh. So you want a multiple of 13 plus a multiple of 15 equals 1. I mean, obviously, one of these numbers is going to have to be negative. If they're both positive, it would be much bigger than 1. If they're both negative, it would be negative. So one's going to be positive, one's going to be negative. So,
How about 7 and -6?
well, let's see. So if you start looking at the multiples of 13, 13, 26, 39, 52, 65, 78, 91, 104, 117. Those are the first multiples of 13. If you look at multiples of 15, 15, 30, 45, 60, 75, 90, 105. Is this right? So 90 and 91, they just differ by 1. So this is 1, 2, 3, 4, 5, 6, 7. So it looks like I
7
take x equal to 7
and
and
y equals
y equal to
-6.
-6. 13 times 7 plus 15 times -6 is equal to 1. So that's one solution of this equation.
Yeah.
It also looks like this is a solution. If I take x equal to -8 and y equal to 7, 13 times -8 plus 15 times 7, this is -104 plus 105. This is also equal to 1. So this is actually, I just found 2 solutions of this, which is interesting.
Wait, hello, Professor?
Yeah,
Wait, where did you get x equals 7, x equals -6?
oh, in the first solution, x equals 7, y equals -6.
Yeah.
How did I find that?
Yeah.
Well, I was looking at the multiples of 13. Here they are.
Yeah.
And the multiples of 15.
Yeah.
And I observed that here's a multiple of 13, here's a multiple of 15, and they differ by 1. Because 91 minus 90 is 1. So 90 is 6 times 15, and 91 is 7 times 15, 7 times 13. So 13 times 7 minus 6 times 15, which is the same as plus minus 6 times 15, that's equal to 1. I just made this little table and looked at it.
And x equals -8, you did
And I also was like, because I continued along this table, here I found 2 other numbers that differ by 1. I have 104 here, 105 here. This is
oh yeah.
8 times 13. This is 7 times 13. So 13 times minus 8 plus 15 times 7, that's minus 104 plus 105, that's also equal to 1.
Okay, that makes sense.
So these two I put in here.
Okay. Okay, thank you.
Again, if I use the results of the next section, I could also get the same result from the Euclidean algorithm. So if I wanted to find the greatest common divisor of 15 and 13 by the Euclidean algorithm, 15 is 13 times 1 plus 2. 13 is 2 times 6 plus 1. So this says that 1 is 13 minus 2 times 6. But 2 is 15 minus 13. So that's the same as 15 minus 13 times 6. This is 13 plus 15 times minus 6 plus 13 times 6. 1 times 13, 6 times 13. That's 13 times 7 plus 15 times minus 6. So I could also have gotten this from the Euclidean algorithm machine.
Professor, can we do homework 4, problem number 3?
I'm sorry, do problem
Homework
4 on this page?
Problem 3 on homework number 4, section 3.
With the numbers 1197 and 14280.
Yeah.
Oh, okay. So this is in section 1.3, which is on the Euclidean algorithm. And problem number 3 is to use the Euclidean algorithm to compute the greatest common divisor of 1197 and 14280. And to express it as a linear and to express this greatest common divisor as a linear combination. So I take 14280. If I divide it by 1197, what is the quotient? So if I were to take 14280 and divide by 1197, I get 11 plus some remainder. What is the remainder? 14,280 minus 1197 times 11 is 1113. So that's the remainder. Then I take 1197, I divide it by 1113. This clearly goes in once, and it leaves a remainder of, I think, 84. So this is 1113 times 1 plus 84. Then I take 1,113, I divide it by 84. That goes in 13 times. And 1,113 minus 84 times 13 gives me a remainder of 21. And if I take 84 and I divide it by 21, that goes in exactly 4 times, has a 0 remainder. So the last positive remainder is 21. So this greatest common divisor is equal to 21.
Professor, 84 times 13. Is that 84 times 13?
Yeah.
It's 1092. Plus-
Sorry?
Oh, okay, I see. Plus 21, okay.
And then we have to express this greatest common divisor as a linear combination of these two numbers. So we work backwards from the Euclidean algorithm. 21 is equal to 1113 minus 84 times 13. This is 1113 minus, and 84 is 1197 minus 1113 times 13. I'm just replacing 84 by this. And here what I have is 1113 plus 1113 times 13. That's 1113 times 14 minus 1197 times 13. But 1113 is this minus this. 1113 is 14,280 minus 1197 times 11. And I'm multiplying that by 14 minus 1197 times 13. So this is 14,280 times 14. And here I have 1197 times what? 14 times 11 and 13.
Where you got 14?
So here I have 1113. And here I have 1113. Minus times minus is plus. This is 1113 plus 13 times 1113. 13 plus 1 is 14. Right? This is 1113 times 1. This is 1113 times 13. 1 plus 13 is 14.
That's 1197 minus 1113 times 13.
Oh, and then there's also, right, and minus 1197 times 13. Yes. So if I put this together, what I get is 21 is 14,280 times 14 minus 1197 times 167. So let me just use my calculator or computer to check that this is correct. 14,280 times 14 minus 1197 times 167 is 21. So this is correct. If I want to write this greatest common divisor 21 as a linear combination 14,280x plus 1197y, solution is x equal 14, y equals minus 167. Minus 167.
Now you got 167.
11 times 14 plus 13.
11 times 14. You said 11 times 14 times
11
13.
times 14 plus 13. Here I have 1197. Here I have 1197. I have 1197 times 11 times 14 and 1197 times 13. So I take 11 times 14, 154, plus 13 is 167. And there's a minus sign in front of them.
At the last part, is that a plus? Or
Well,
21 equals 14280?
it's either it's plus times minus 167 if you like.
Thank you.
So I'm writing 21 as 14,280x plus 1197y. X equals 14, y equals minus 167. Let's see, I can do one more homework problem if anyone has one that they would like me to like to see me do.
Um,
Let me do one more computational one where I have to find the simple continued fraction. Let's just start with number 1. So if I take the numbers 35 and 91, I want to find the
that
greatest
one
common
is not
divisor.
part of the homework.
Sorry?
Number one was not part of the homework.
Um,
Can we do a number 4?
in section 1.3 on the Euclidean algorithm, number 1 was part of the homework.
No, homework 4, it says exercises 3, 4, 5, 10, 11,
Yeah,
12, and
this was homework 3.
that's
And,
homework.
in homework 3, it has problems 1 and 2 from section 1.3. So let me do number 1.
Oh,
Find the greatest common divisor and then use that to find the simple continued fraction. So if I take 91, I divide it by 35, I get a quotient of 2 and a remainder of 21. If I take 35 and I divide it by 21, I get a quotient of 1 and a remainder of 14. If I take 21 and I divide it by 14, I get a quotient of 1 and a remainder of 7. If I take 14, I divide it by 7, I get a quotient of 2 and a remainder of 0. So the greatest common divisor is the last positive remainder is 7. And then I want to write 91 over 35 as a simple continued fraction. So if I take this first equation, I divide by 35, I get 2 plus 21 over 35, which is 2 plus 1 over 35 over 21, which is 2 plus 1 over. If I take the second equation and I divide by 21, I get 1 plus 14 over 21, which is 2 plus 1 over 1 plus 1 over 21 over 14. And if I take the third equation, 2 plus 1 over 1 plus 1 over 21 over 14 is 1 plus 7 over 14, which is 2 plus 1 over 1 plus 1 over 1 plus 1 over 2. So this is the continued fraction, or in our concise notation, 91 over 35 as a continued fraction is 2,112, which are exactly the partial quotients that you see in the Euclidean algorithm. All right. So this is good. Maybe I'll spend more time.
Professor.
Yes.
So, for this problem and the one we did before, the questions are the same questions, but different numbers, but you solved it in two different ways. Why you didn't do it the same way as this one?
No. In the problem I just did, it was a different problem. It was in the problem 3, it was to compute the greatest common divisor and to write it as a linear combination of the two numbers. Right? In problem 1, it was to compute the greatest common divisor and then to compute the continued fraction. So in the first part of each problem, it was the Euclidean algorithm. That's what I did. And in the second part, in the first problem, in this problem, it was to compute a continued fraction. And the other problem is to do something else. You know, the rule is answer the question that you're being asked. So here I'm asked to compute a continued fraction. In number 3, which I did first, I was not asked to compute a continued fraction.
The professor?
Yeah,
For 91 over 30, I didn't get the first step. Why is it 2 plus 21 over 35?
here.
Yeah.
So I have this equation, 91 is 35 times 2 plus 21.
Yeah.
Right? No, let me write it down. 91 equals 35 times 2 plus 21. Divide by 35. 35 over 35 is 2 plus 21 over 35.
Okay.
I'm just taking this first equation, dividing by 35.
Okay. And then the second one, you do the second equation.
Yeah.
Okay.
And then I
Okay.
took this equation and I divided it by 21.
Okay. Okay.
Right.
Okay.
Can we do number 5, please? That's a proof.
Well, so you have to understand the notation. So this is number 5. If I have this continued fraction, this is defined to be A0 plus 1 over A1 plus 1 over A2 plus 1 over A3 plus going down to finally I get 1 over A sub n. And if I look at this is equal to A0 plus, well, it's 1 over this. And this is 1 over this. This is the continued fraction A1, A2 up to A sub n. That's the proof. Like if I had 7, 2, 3, 5, this is 7 plus 1 over 2 plus 1 over 3 plus 1 over 5. If I just had 2, 3, 5, that's 2 plus 1 over 3 plus 1 over 5. And if I look, I see that's exactly what I have here. So this is equal to 7 plus 1 over 2, 3, 5. That's an example.
So this is the proof.
This is the proof.
That's all we have to do for that problem.
Yes. This is the example. Just to see with numbers what this means.
Oh, the professor,
Yeah,
what do you mean by a counterexample? Is it,
you make an assertion that's false, there should be a counterexample.
oh, okay. So it's like this, but
No, this is an example. This is not a counterexample. This is
Oh.
something which confirms the truth of the statement.
a
This is not
counterexample.
a counterexample, this is an example.
Oh, okay.
Okay. That's it for today. Next week, there's no class on Monday. So the next class is a week from today. But there are some problem sessions between now and next Wednesday. So if you have questions about homework or anything else, log into a problem session and you're free to ask anything you like. Okay, that's it. Bye all.
Professor, is
Yeah.
that a sub 3 plus
Dot,
like
just all the other stuff that would be involved in the continued fraction. It can be arbitrarily long.
okay.
They're just dots. It just means you keep on going.
And then that's a 1 over a sub n.
Yeah. That's an is the last term in this sequence. Like here, in this example, n is equal to 3.
Yeah.
A0, A1, A2, A3.
Okay.
Okay. Bye all.
Bye. Thank you.